Well, hello and welcome you to Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you today as it is every day here in my virtual classroom. Okay, step on inside, and this one is going to be, it shouldn't be too funky, but there are some things to it that I want to kind of let you know. So this is a review and an overview of this whole unit here in Integrated Math 3, where we've been looking at graphing polynomials, using polynomial functions with operations, taking their inverses, checking for evens and odds. Actually, now that I think about it, I think that's absent from here, so I need to make note of that somehow. The even odd stuff seems to be absent from this. This is a review. In this review, it has 30 some odd questions. I got to check officially. I think 36. I can't remember, but it has several questions there. But I want to make some modifications to this. This wasn't my official review. I did give it to my students, and that's why I'm making the video, of course, but it was made from another teacher or generated as problems from another teacher. Some of the problems, we didn't actually do when it came to, there's some radicals, there's some square roots and things like that. We can use some of them by nature of how we transform functions, and I'm going to talk about that. But I will propose different problems here and there and go, here's an alternate version of what we can do if we turn it from a square root to a quadratic, or something like that. I know I want to do that. I've not done this problem set yet, so sorry if I get caught off guard with anything. I know I've scanned it and looked at the problem types to know what to do, but I will deliver the goods as best as possible. Like I said, I do believe and I do recall that we didn't have even and odd on here. I don't know. We're going to have to maybe just look back at an older video for even and odd functions, or maybe I can call attention to something that is like this right here. I know this is an odd function right here. Maybe I can just call attention to what they are just a little bit for you. Okay, describe the transformations necessary to transform the graph of f of x, the solid line, into that of g of x, the dashed line. Now, one thing that I remember I wanted to say about this problem, or this particular kind of problem, is that it's easier to talk about transformations if you have specific points to look at. And although this has the curve, and all the points are on the curve, let's look at some specific points with this as well. Like that's crossing at 0, 0, and 1, 1, and 2, 8. -1, -1, and -2, -8. This is very much, this graph, that's f of x equals x cubed. This is a cubic function right there. Literally, straight to the point. 1 cubed is 1, 2 cubed is 8, all that stuff. That's what this is. And this doesn't have to be dotted or whatever. I think the point is if you print this out, it'll be in black and white, so you want to be able to tell one from the other. But to us, it might as well be a solid line. But you can see that it's green. There's a specific point right there. There's a specific point. That doesn't specifically hit that point, I'm going to mention. And it hits that point, and it looks like this point right here. Also a cubic function, right? As that's what this thing is. You're taking f of x, and you're trying to figure out what the g of x is from f of x. Now, here's the thing. You maybe wouldn't have known that this was actually x cubed. You would have just known this was a black box f of x function. Like, we're just going to call it f of x. And describe the transformations right here necessary to transform this thing. What you probably notice is this graph did not reorient itself. It didn't reflect in any sort of way or have any sort of inversion principles. And it didn't seem to stretch or compress vertically or horizontally. It just moved. It just translated. This point seemed to go from here to there, and this point went from here to there, all in a very congruent fashion. These are one-to-one when it comes to, like, these are isometric. It just moved over. So how far did it move? What did it do? It went 3 units to the right and 1 unit up. That was called a translation. This point also went 3 units to the right and 1 unit up like that, etc., etc., etc. Just goes 3 over, 1 up. And this would have went 3 over and 1 up as well, and then it would have ended up right there. That's why I said that that point didn't really seem to get hit. And that's what we're going to do. We're going to describe this thing right here as far as the transformation goes. And, you can list items. If it does, it says describe the transformations necessary. So really, there are only 2 things that happen, and I think I can use them with the same verb, translate. Translate f of x, this is what g of x is going to be. You're going to translate f of x 3 units right and 1 unit up. And what that tells you is that every single point on this graph follows that rule. Now, they said describe the transformations, not write the equation. I believe write the equations comes here. Write g of x in terms of f of x. That's numbers 3 and 4. Let's go ahead and write it out anyway. I think the value is within that you can see both, especially if you get different answers there. So here I'm going to say g of x. This is not part of your official answer, but I'll write it. It's f of x minus 3 plus 1. And if you are aware in this notion here, the way that we go about saying that is g of x equals, I probably should have written this first, a times f of b times x minus h plus k. And if you're new to this, I'm not going to reteach a lot of this stuff, but what I'll state is all of these, the a, the b, the h, and the k, are transformative parameters. Based on what you can see here, you can create transformations from this. A is something that multiplies with your function. It affects your y. It vertically stretches or compresses or reflects your function. B is within the function itself, but it does multiply by the x value, which has to do with factor, compression, stretches, or reflections of x, of the horizontal components. H is a horizontal translation. When you add or subtract something from there, you're asking how x needs to move to correspond to that. So H is a horizontal translation. That's what this minus 3 is doing right here. When we translate 3 units right, you see x minus 3. Now the minus h is there for certain reasons. You have to flip that value right there. And because h is 3, a positive 3, you're going to be subtracting that positive 3, x minus h. The plus k is something that affects the y again. Your f of x is going to be plus k. F of x is y plus k or minus k, whatever it is. In this case, a plus 1 means it's a vertical translation, 1 unit up. So that plus 1 is the k. H is 3. K is 1. You get that equation right there. Again, not something you were supposed to be asked just yet. And really, if I knew this was x cubed, I would have even went one step further. I would have said g of x equals, I'm spending a long time on number 1 to do all this, x minus 3 quantity cubed plus 1. That's literally what this graph is, cubed plus 1. And you know what? There might be a reason I need to write that because I don't know if we're actually graphing any cubics. I think we might be, but there's that one right there. That's what it'll look like. All right, a lot on number 1 that hopefully you got to absorb there, and I get to keep moving forward. But this is all, see, here's what this review is to me. And I'm just going to go and say this before I keep moving on. For me, the review it's not necessarily going to appear like the test, so to speak, when it comes to my own students. I mean, these questions might be harder, they might be easier, they might be presented differently. For us, though, this review shows a series of questions that says these are attainably achievable. You can answer them based on the information that's been learned in the past. That doesn't necessarily mean that I have to divulge straight into what that one answer is. I want to cover this basis and still teach, meanwhile, actually covering it. So it's a solution guide, yeah, but to what extent? To the extent that any question around this could have been asked in any sort of way. It didn't have to ask, write it with f of x. It could have said, do it with the function, x cubed. It didn't have to say, describe the transformations. It could have said, write the equation. And it could have asked, is this function, the blue one, even or odd? Or neither? And I would have said, this is called an odd function. So before I go into number 2, what makes this an odd function? The fact that whenever you plug in a negative x as an input, you get the opposite y value out. When I plug in 1 here, I get positive 1. When I plug in negative 1 here, I get negative 1. When I plug in positive 2, I get positive 8. Negative 2, I get negative 8. When I plug in the opposite value of x, I'm getting the opposite y out, something like that. That's what odd functions do. They are symmetric, they're symmetric across the origin. So it's an odd function as well. All right, that's a lot to say here. Let's go on to number 2. Number 2 has its own tricks up its sleeve here. And let's also plot some points that this has. It has 0, 0, 1, 1, 4, 2, and it doesn't quite hit. It doesn't hit 8, 3. I'm guessing it hits 9, 3 because this very much looks like a square root function. Now, even though we're not graphing these, it's that kind of thing. Like, who cares, right? At least for this stuff right here. We're not actually going to talk about square root of x, but the square root of 1 is 1, the square root of 4 is 2, the square root of 9 is 3. So at the very least, you can just confirm that it is that. That was the parent function. How does this transform? And I'll have you know, because I don't know what the answer things are, but I'll have you know that you could answer things more than one way based on whether you're talking about horizontal stretches and compressions or vertical stretches and compressions or a combination of both. I bet they can do both, and I can try and describe both if they exist. Some are probably better answers than others here, but I see it's hitting there. Do you guys see it hitting anywhere else specific? It might be. I'm guessing it's going through that -8, -4. It looks like it's hitting that a little more than something else. I can't guarantee it, but after I describe the transformations, it might actually confirm or deny whether it was. But we get some of those points here. Now I'll say this. 0, 0 stayed the same right here when you're looking at that guy. So it's unlikely that there was a translation that happened. Unlike this, where my centerpiece, I have to call that the center right there. It probably is called the center. Where the center of that cubic moved over and translated, this 0, 0 did not. That kind of frame of reference, the start of your domain, that did not actually have a shift on it. And you don't want to say that these other points shifted, left 3 and down 3 and things like that, because this didn't go left 3 and down 3 right there. But what I could potentially conjecture is that this point might correspond to that point right there, perhaps, as in I can do transformations to correspond that point and say what's happening. So I'm seeing two different ways I can talk about these transformations. The first thing I want to mention here is the way that it totally reoriented itself. Besides stretches and stuff, consider taking this blue thing here and flipping it on its head so that, kind of like the cubic, that this thing would have gone 1, 1 down here and 4, 2, down like that, and kind of just have the other version of this graph that's going that direction, right? It didn't stretch or compress, but it did reflect. How do we get the graph to reflect going this way? Well, it had to have reflected going another way as well. Maybe this blue had to reflect across the y-axis like that first. It had to flip that way, and then it flips over. So the first two transformations that I want to mention before anything else here, the first two that I like to mention are, let me do that one more time. I guess I have to shrink the text each time here. So I'd like to reflect, see, I don't know why that text did that. I'd like to reflect f of x across two axes, the y-axis and the x-axis. By reflecting across them, it mirrors it in such a way that it makes it go, I don't want to say backwards, but it goes from right to left like that, and then it goes from up to down like that. Reflect across the y-axis, boom, boom, and then reflect across the x-axis, boom, boom. That turns it into this purple version. Not the green version, but the purple version. It goes from blue to red, red to purple. And you could have gone across x and then y. It doesn't matter which order. You're going to end up in the same spot. It ends up being this kind of a rotation, if you will. So that's the first thing that we're going to mention here. And yeah, this is going to take a while in recording this stuff, guys. I'm sorry. I think the first time we talk about this, I think it does kind of have to be taught. Okay, it's fine to be the different font. But anyway, that's one thing we do. Now, the next thing is with regard to the actual, what do you call it? The actual, why does this not? Give me one sec. I guess I have to rewrite this thing. I don't know what's happening here. But the actual, the stretches, the compressions, the what have yous. So let's try that one more time here. Give me one moment. Reflect f of x across x, whatever, x-axis and y-axis and x-axis, all the same thing, right? Okay, the other things have to do with stretches and compressions. Now, there are two different ways we can look at it, and I really only am looking at purple now because I have already applied those two transformations. So I'm going to ignore blue and look at what's purple doing, how can I make purple turn into green? Okay, so it's like we can see this one of two ways. We can say, can I turn this point into this point by doing transformations, stretches, or something? And the answer is yes, I could. And that's one way we could go about it. Or can I turn this point into this point using transformations and stuff as well? And I could say yes to that too. In fact, I kind of like this version more because it would take a single transformation to make it happen. If I want to go from this purple to this green, notice that the y's are the same height. That means I don't have to stretch or compress vertically. I only have to stretch or compress horizontally. I can take the purple and I can squeeze it inward into green. And these points matter here. This purple point is -4, -2. The green point right here is -2, -2. How do we go from -4 on x to -2 on y? Not by a translation, remember. We're not translating, but by shrinking, by squishing it down. It's becoming half the size. It's becoming half the size if we do that. And just keep in mind, guys, this graph goes forever, right? It keeps going left just like the green keeps going left. And eventually it hits some height right here where this should be half of its size in the x direction as well. If this is truly -8, -4, then this point out here should be -16, -4, right? Which means we could take half that size as well. So the way that I'd probably describe this best is I'd talk about a horizontal compression, and really a horizontal compression only. Horizontally compress f of x still by a factor of, you can put us one of two ways. I'm going to try and be consistent and say 1/2. You can argue saying horizontally compressed by a factor of 2. The reason why horizontally, that's not how you spell horizontally. Horizontally. There we go. Compressed by a factor of 1/2. You could say by a factor of 2, meaning make it twice as small, right? And that would probably be more grammatically correct when it comes to the math stuff. But anytime you've heard me say this, I'm doing two things. I'm using 1/2 to describe compression, and I'm using the word compression to describe the transformation, if that makes sense. When A is less than 1 or when B is less than 1, we go ahead and say that. Sorry, not B. But you know what I mean when we use those numbers that way. You could say 1. Anyway, I'm going to leave it like that. All right, so that's one way we could answer it. Alternatively, I could have said this, and I'm only going to say it out loud. I won't write it. We could have taken purple and turned it into green right here. We could have stretched it a little bit. We could have doubled its stretching, and we could have doubled its vertical stretching as well. We could have said horizontally stretched by a factor of 2 and vertically stretched by a factor of 2, and it would have doubled it. And then would this point have worked out that way? We would have went from -4 to -8. That would have been a horizontal stretch by a factor of 2. And from -2 to -4, vertical stretch by a factor of 2. Yeah, that point should be at -8, -4, and we would have been good. But I'm going to go ahead with that description there. We spent a long time on this already. What I will show you as one more thing when it comes to g of x, as far as an equation goes, it could have been g of x equals. If we reflect across the x-axis and y-axis, reflecting across the x-axis is making a be negative, and it's literally a -1, like that. The square root function would then go into play, and then we talk about b right here. Compression by a factor of 1/2 actually does turn b into a 2. A 2 meaning that it would, whenever b is larger, right, it's a reciprocal effect. If b was 4, you shrink it 4 times. If b was 1/3, you grow it 3 times. Kind of weird. The negative is reflecting across the y-axis there, and then just x. There's no translation. And that would have been the answer. And no, these negatives cannot cancel each other out. This one flips it over x. This one flips it over y. Guys, I'm making the video longer than I ever planned to be. These problems have a lot of descriptors within them, and I think it can speed up some of the other portions of transformations when I talk about them more. But all these are super pertinent to the description and your discovery on how to describe it, I do believe. Yes, I could have solved those problems within, a minute myself. Heck, I did 278 factoring problems within 2 hours. Yes, but, right here, we're trying to describe as much as we can. Okay, this one. Write g of x in terms of f of x solid line. Now, this is the one where they do want us to write the equations of them. And so, this is a square root. So maybe this is one that I transform with my own students. And I'd say I could turn it into a quadratic, and we could also do that as well. So maybe we talk about this one. Maybe I make a quadratic version of that after, and then we play with that. So this is a square root graph, right? So this is f of x equals square root of x. But maybe you didn't know that. Oh, you know what? No, I take it back. We didn't have to know this. We didn't have to know this. They just said in terms of f of x. That's fine. But it is another square root graph, just so you're aware. Oh, I'm sorry. I didn't want to take square root here then. I should have said this. This is messy. This is me not doing the thing beforehand. -2x like that. There we go. That's what I wanted to say there. So I didn't use a square root. Negative f of -2x. And those negatives can't cancel each other out. Okay, so down here. You didn't have to know that it was a square root here, but I'm telling you that it is. Anyway, this is the same thing. There's that 1, 1 and 4, 2, and it doesn't hit 8, 3, but it would hit 9, 3. And then we have these points right here, which is that one and that one. And it looks like that doesn't hit anything else either. So this looks a lot like the previous problem as far as what happened with the scaling. One thing we probably want to talk about first, even though it doesn't happen first because reasons, is the translation. That this graph, this point translates into there. So it goes one right and one down. I like to mention translations first when it comes to us graphing, but when it comes to descriptions, we have to mention translations last. I will explain why. But I do want to mention that these translations do occur, and if we line these up in 1, 2, 3, 4, 1, 2, 3, 4, 1, 2. When we see it this way, that does help us understand what happens to the points next. So if I ignore this blue and look at this blue, maybe I should turn it purple. If I ignore one blue and look at the purple right there, then you can start to see that, what happens after that. So there's a translation of one right, one down. We are going to describe that because we're going to write it in the equation. But what else happens? We just saw this before, right? A horizontal compression. This blue turns into that green by horizontally compressing by a factor of 1/2. Or you could say that this point horizontally stretched by a factor of 2 and vertically stretched by a factor of 2. I'm going to do the former. So I'm going to mention the horizontal compression first. Technically, that's what you would do first, and I will explain why after I type this out. even though we're supposed to write the equation, right? Horizontally compress by a factor of 1/2. And also translate 1 unit right and 1 unit down. This is all about f of x. Okay. Also, I have to write the equation. So this would be g of x equals. So the horizontal compression, that's not a, and we didn't flip anything over there. So this is f of horizontally compressed by a factor of 1/2. Remember, that's going to be 2. Translate 1 unit right inside these parentheses. Here's your x minus h, and that's the end of the function. And then plus k, 1 unit down, is going to be minus 1 like that. So that's how I should be writing this guy right here. Okay. Why do I have to talk about horizontal compression before I talk about translation? And maybe I can't use this graph because it's a little cluttered, but I just want to give another example. Well, okay, yes, I can. Let's say I did say this first. Let's say I said translate it 1 unit right and then 1 unit down. Let's say I mentioned that first. Boom, step 1. Translate 1 unit right, 1 unit down. And then I say step 2, horizontally compress by a factor of 1/2. Then you would have to take this point and compress it by a factor of 1/2. This wouldn't be at 1 negative 1 anymore. Now it would be at 1/2 negative 1. I would have horizontally compressed it and it would have moved. So if you keep things where they're at and I horizontally compress, say this thing first, 0, 0 stays at 0, 0. 1, 1 would turn into that guy right there. That's fine because when I then shift these over, where do they go? This goes here and this goes there. So, you want to do the compressions and stretches first and the reflections first. You want to treat A and B first when you describe it because that's what we would literally do first and we translate every piece after. When I graph them, what I do instead is I start with the translation because when I graph everything in relation to my translation, and then I just say, then therefore everything translated on its own automatically. I don't translate after the fact. So there's kind of a little difference there. And that's, that's a little teaching thing, right? That's a personal touch that a teacher can give that an online thing couldn't. They would say plug values in and make it work. Or, I don't know, do something like that. Now, this was a square root graph. I'm going to go and leave it as a square root graph because we didn't have to talk about quadratics at all. Okay, second one right here. So let's look at some of the points that there are. So there's this guy right here, and this guy looks like the cubic from before. I'm going way too long in this video, guys. Apologies. Sorry, that did totally not hit that point right there. That totally hit this point right here. And then that guy, and then that guy right here. Green, let's see this. It definitely hits there as my center. Looks like a translation. And then looks like it definitely hits that guy. So and it doesn't seem to hit anything before that's of value to me, but we can talk about some things when it comes to potential fractions here. Because really, again, the question is, would you rather, and I don't know if I'm in the way of the graph, I'm not, would you rather mention 2 transformations in terms of stretching and compressing, or just 1? So I'm going to take a look at this as best as I can as far as what if I translated this green over into the blue, what would it actually look like? So let me draw over this for a second so we can compare them. You notice that there's a translation. Sorry about that. You notice that there's a translation in one thing for sure. For sure. So for sure there's like the translation, right? So if I move this thing over like that. But then what else is happening? See, what I see, you could go like, oh, let's turn this piece into this piece right here by horizontally stretching by a factor of 2 and then vertically stretching by a factor of 4. I wouldn't rather do 2 pieces if I could just do 1. Let's turn this blue into this green right here because they have the same x value. They share the same x, so let's vertically compress this thing. This turns from 8 into 4. Let's vertically compress by a factor of 1/2. That's my preference. 1 transformation instead of 2 when it comes to the stretches and compressions. And that's what I'm seeing there. The center shifted 3 units to the right, but everything also vertically compresses if you consider that this point is a transformation of that point right there, as opposed to this point is 2 transformations of that. So as far as descriptions go, and of course that's not what the official answer is, the descriptions aren't, but writing the equation. But we could say, and I got to do the compression first, vertically, even though it doesn't seem to affect because horizontal translation only, vertically compress by a factor of 1/2. And then also, by the way, translate 3 units to the right. So as far as an equation goes, and the equation is the answer here, and I really got to speed up after this. I think because these are all kind of new, I really got to talk about it a little bit more. This would be g of x equals, vertically compressed, that's a. A value is 1/2. 1/2 times f of x minus 3. 3 units to the right. That's my look there. Alternative answers, right? What I was mentioning before. What if we did say these alternatively? Now I'll give the alternatively so. We could have said here the translations would have been the same, one right, one down, but we would have, what did I say? We would have gone from this point to this point here. So we would have doubled and doubled, right? We would have horizontally stretched and horizontally and vertically stretched. So we could have also had alternatively vertically stretched, vertically doubled and horizontally doubled, which would have been a 1/2 there. So this is an alternative answer. I don't like that one as much, but that's something you could have done. And alternatively here, we could have done the same-ish. We could have said, taken this point and made it into that point. We could have horizontally doubled and vertically quadrupled. So vertically quadruple and horizontally double. That is an alternative answer, not one that I love. See, that would have been 2 transformations there instead of just 1. Okay, I'm moving forward. If you listen to all that, maybe you learned a lot. Or, I'm not sure. But I'm going to keep moving forward here. All right, describe the transformations necessary to transform the graph of f of x into that of g of x. Okay. F of x equals x cubed, g of x equals this guy right here. Now, one thing I'm going to do with this g of x is that if you want your true b value and your true h value and all that kind of stuff, when you look at this transformation idea that looks like g of x equals a times f of b times the quantity x minus h plus k, I said b times the quantity of x minus h. This x has to be a 1x right there. It has to be a 1x in order to reveal the true h value. This h is not 6. The thing that's inside the function has to do with b and h, but the h is not 6. I have to factor that 3 out, not of the cubic, but of the 3x minus 6. I have to factor the 3 out, and inside you get x minus 2, like that. This reveals your true, this is your b, it was 3. This reveals your true h. As far as this thing goes, you are truly asking yourself, what value of x do you have to plug in to make this guy become 0? And the answer is 2. Even right here, 3 times 2 minus 6 is 0. What value do you have to plug in there? You have to plug in 2. That's the h value right there. So the b is 3, the h is 2, and this can help us describe the transformations right here. With h being 2, that does say that we do translate this thing 3 units to the right for f of x. And it didn't matter if this was a cubic or anything else. That doesn't change. And by the way, I don't mention translation first, but I'm saying that h will say we translate 3 units to the right. The b value of 3 means that we are going to horizontally, not stretch. Remember, b is backwards. Sorry about that. But we are going to horizontally compress f of x by a factor of 3. Of 1/3. Of 1/3. 3 times smaller, right? That's one thing. And then there are translations. Translate f of x 2 units to the right, because it's minus 2. Again, backwards. 2 units right, and 3 units up. That's what the k value is doing. And that didn't change there. So mention b first, a and b first before h and k, and there it is. All right, the second one is the same kind of stuff, and it's not much different. I think there's one more instruction, because there's an a value right there, but the b has to factor out in the same way as before. This is going to be g of x equals 3 times the square root of 2 times x minus 4, like that, and then plus 1. Okay. So there is an a of 3, a b of 2, an h of 4, and a k of 1. 3, 2, 4, 1. So how do we describe that right there? We can say, first let's talk about a, then let's talk about b, then h, then k. Vertically stretch f of x by a factor of 3. It's going to be 3 times taller. Horizontally, again, compress. I'm sorry that these aren't too diverse here. I wish I had a 1/2 to say, but horizontally compressed by a factor of 1/2. I don't know if my picture's getting in the way here. H is 4. Translate 4 units right, and k is 1, and 1 unit up. 1 units. 1 unit 1. 1 unit up. There you go. All right, and that's what we can do the graph. Okay, now they're going to sketch some graphs here. Now, I'm not going to I'm not going to write out the descriptions of the transformations, but I'm going to go ahead and do those transformations with it. Now, this is a cubic function right here, and that will be important for how we graph this thing. The original cubic would have been 1, 1, 2, 8, like that. -1, -1, -2, -8. And I'm not going to have this stayed out and drawn. I just want you to hear those numbers, 1, 1, 2, 8, -1, -1, etc. We're going to apply those if there are any stretches ever, or things like that. But this is my h, and this is my k right here, and that the h is actually 2 units right, and the k is 3 units down. This center piece is going to be 2 units right, 3 units down. That is where that center portion of the cubic function is. The a value is 1, the b value is 1. That means no horizontal stretches, compressions, vertical stretches or compressions, or any reflections of any sort. That means that you take the cubic that we just had, and that's what we're going to do. Translate 2 units right, 3 units down. That's where I use this as a reference point, and from here I do my 1, 1, 1 cubed is 1, and 2, 8, 2 cubed is 8, like that. -1, -1, and -2, -8 doesn't quite fit down there. That gets a little low. So I'm just going to go ahead and graph it from this. It's going to hit through, try that again. It's going to hit through this guy right here, and here, and cubically go on through, and never quite hit that guy down there. Try to keep it function-like right there. And there's your graph. All right, number 8. This is one of those ones where I'm going to say this brief with the square root stuff, and I'm going to change it into a quadratic after. I just will. So there's one version that I'm going to do that's in purple, and there's one version that I'm going to do that's in green. I'm going to make this one as well. 2 times, let's just say, squared. Let's square this guy. Even with the negative in there, sure, I can talk about that, and how it pertains to the square root thing, and how one function is different than the other. So with regard to a square root function right here, the original square root stuff is square root of 0 is 0, square root of 1 is 1, square root of 4 is 2, like that, and the graph will just go this way. Boom. Like that. We're going to transform that stuff. So there's a 2, which means we're going to vertically stretch it. Everything's going to be twice as tall. There's a negative inside, and that's your b. A is 2, but b is -1. That means this thing is going to reflect over the y-axis. It's going to flip over. And then this h here is 2, which means we're going to translate this thing 2 units to the right. Now I start with the translation. Despite the fact things flip over, I'm going to already have accounted for that flip over here. So I know in my head I'm flipping over. That's great. But I'm going to shift 2 units to the right. So again, when I say now flip this thing over the y-axis, I'm not going to just move this point over here. I'm going to keep it here and know that I'm going to go to the left. The flip over already happened in my eyes. Everything's going to be twice as tall as we go to the left. So instead of 1, 1, 4, 2, 9, 3, as the square root of 9 is 3, I'm going to go 1, 2. I'm going to double my height right there. Instead of 1, 1, it's 1, 2. Instead of 4, 2, I'm going to go 4, 4, doubling that height there. You know, the square root of 9 is 3, but let's double that 3 and get 6. And that's what this graph is going to look like right here. It's going to go to the left, it's going to be twice as tall, and of course everything is translated 2 units to the right. And everything is translated 2 units to the right, guys. This point would have been over here. This point would have been over here. This point would have been over here. But I translated them because I did everything in reference to my actual square root guy. So that's one graph right there. Let's go ahead and do the green one now. Let's take a look at this quadratic. And you can do it one of 2 different ways, but a is 2, b is -1, and h is still 2 again. Those did not change. A quadratic graph would have started at the vertex right here. 1 squared is 1, 2 squared is 4, 3 squared is 9, probably up there. And then -1 squared is 1, -2 squared is 4, -3 squared is 9. This would have been the original graph like that. But then we would transform these things. We would shift the vertex 2 units to the right, just like this right there. Boom. We would have flipped this thing over in B. I'll tell you what, a quadratic flipped over, the y-axis does not change. That's what makes a quadratic x squared an even function, because symmetry right there. So that negative literally does nothing. I'll show you another bit of that in a second. And we're going to make it twice as tall. So instead of 1 squared is 1, 1 squared is 1 times 2. Instead of 2 squared is 4, 2 squared is 4 times 2. We're going to make everything twice as tall right here. 1, 2, 2, 8, like that. And the parabola will get a little tall. Still a U shape. And it's going to look like that right there. So that's an alternate version of that. Now the thing I wanted to show you here was this whole negative guy. And I said that it doesn't actually change the graph. You know how this one went to the left instead of going to the right? This thing, that's because it flips over the, how do I do this? This thing flips over the y-axis like that. Well, a U-shape flips over and it stays the same, right? Now, how can I also use this b in different ways? This is g of x equals, sorry, let's just look at the inside part. Let's look at the negative with the x minus 2 quantity squared. That means negative 1 times x minus 2 quantity squared, which means I can square each part of this. Square the negative 1 and square the x minus 2. Negative 1 squared is just 1. So that just becomes 1 times x minus 2, which means squared, which means that negative 1 squared is positive 1. That means this also could have been rewritten instead as g of x equals 2. 2 times 1 is 2. So 2 times x minus 2 quantity squared. This is equivalent to it. These are the exact same thing. They're the exact same graph. They are the exact same graph. And that means b would have been positive 1, and there would have been no reflection over the y-axis, and you would have still had the same graph. No change would have been made. So kind of interesting, and I might run into that down the line. Number 9 is another square root graph, which I will cater toward when I talk about the squared thing as well. I'm going to make a squared version. So in purple, I'm going to do this one right here. And in green, I'll do g of x equals, I should really call it h of x. I should make it a new thing. But 2x squared like that, and then minus 1. And we'll talk about how a and b can change on that one. A lot of different things we can do here. So let's start with this one, the square root guy. The a is 1, no change. B is 2. So this time we will horizontally compress by a factor of 1/2. Everything will be twice as small, twice as close. The k is negative 1. You can tell that this time it's not h, it's outside of the square root function. So you subtract 1 from the y's, it makes it 1 smaller. The square root generally starts at 0, 0 right there. We're going to shift it 1 unit down like this. And normally it would go 1, 1, 4, 2, 9, 3, like that. But now we're going to shrink horizontally half the size. Instead of 1, 1, we're going to be 1/2, 1. It's going to be twice as small there in the x direction. Instead of 4, 2, it's going to be 2, 2. Half of 4 is 2. Instead of 9, 3, it'll be 4.5, 3. And instead of 16, 4, the square root of 16 and 4 is going to be 8, 4, like that. And I can plot all those points right there. And it does go to the right and it does go upward. And that would be that graph like that. Whoops. So there's that square root graph if you know how to graph square roots. My kiddos might not know how to graph square roots yet. We haven't done those, so we can work on this one right here. We still have a b value of 2 and a k of negative 1, and we can apply the same thing as we did, but for a quadratic, right? The parabola. So instead, the quadratic goes 1, 1, 2, 4, 3, 9, and the other way around. Let's shift it down 1, just like that, boom. And instead of 1, 1, it's going to be 1/2, 1, just like that guy right there. Horizontally compressed by a factor of 1/2. Instead of 2, 4, it's going to be 1, 4. 4 up from that is right there. Instead of 3, 9, and 9 up is going to be right there, it's going to be 1.5, 9. That's half of 3. Very skinny graph right here that would go like that. Very tall, very skinny, very, very, very much. Let's see if I can actually connect through these points here, though. And yeah, that is a U-shape. It might look kind of V-shape-esque, but I promise it's U-shape. Now, alternatively, what could have we done? We could have squared the 2, right? We could have done just like I did from that other one where I squared the negative 1. We could have turned it into 4x squared minus 1. Mr. Robinson, what's the difference between this and that? This is not a b value anymore. This is now an a value. That's a equals 4. The k is still negative 1. That's fine. But a is 4, b is 1. A is 4. Doesn't that change your graph? Wouldn't that make it 4 times taller? Yeah, but check this out. The original graph, if I'm translated down already, we think of 1, 1, 2, 4, things like that, right? Instead of 1, 1, if it's 4 times taller, it would be 1, 4. We have that point right there. Instead of 2, 8, it would have been 2, 16. Instead of 2, 4, it would have been 2, 16. 16 is way up there. We never reached it, 16 up. But that's what it would have eventually hit. So yeah, it does hit 4 times taller like that. And that's what I generally like to do with my quadratics. I don't like b as much. Here you could have done the same thing, only you had to take the square root of 2. The square root of 2 would have been your a value. A square root of 2 as a stretch factor doesn't really work well. You'd have to know what 1.4 times taller is. Apparently that's that number right here. And I wouldn't have liked that as much. That's where I guess I can use my b, I guess. Otherwise I tend to not use b. Okay, number 10 here. G of x equals x plus 1 quantity cubed minus 2. Looks like we're not stretching and stretching the cubics right here. But the h value is -1. We actually get to see a negative here. Remember, that's x. That's x minus -1, quantity cubed like that. So h is -1 there. The k value is -2, and it looks like that's all we're doing. We are translating these things 1 unit left, 2 units down. -1, -2 is our center. And then the a is 1, the b is 1. We're going to go 1 cubed is 1, 2 cubed is 8, and by 8 I mean 8 up from -2. -1 cubed is -1, -2 cubed is -8. Can't really fit it. I'm going to kind of make believe that that's -10 down there. And we go ahead and we graph. So the reason I have to talk on a lot of this is I don't feel like I made recent videos on some of this stuff for transformations, and I think it's very pertinent to have some of these things here. And there's so many alternative ways you can talk about this. I've only done 10 problems. It's been 40 minutes here. There's still some more transformations to go, and then we have some other things beyond it where I want to try and speak faster because I've had recent videos on some of the other things, I do believe. Identify the parent function f of x and write an equation for the function given. I see this snake-like thing. I identify that the parent function, the original, prior to transformation, would have been x cubed. That's the parent function. The original, boom, 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 and snake on through. And then this thing transforms. What we're looking at in blue is our g of x. That's all the transformations that happen. So we got to ask ourselves, what went on from this graph right here, boom, 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 to this graph right here? What kinds of things do you see? I see, and there are two different ways you can talk about this, because if you flip a cubic, you know what? Let me draw it a little more accurately right here, because I'm going to actually do this. If you take a cubic and flip it over, Mr. Robinson, which way are you talking about flipping over? Left, right, or up, down? Yes. If you flip it over left, right, watch this. I'm going to hit this button that says flip left, right. You don't know where, you can't see it, but it's right. I'm going to flip it left, right. Boom. Hey, it looks like that, right? I mean, it's translated, but it looks like that. Okay. Now I'm going to flip it up and down. You might not know that I'm going to do this, but I'm going to flip it up and down. Boom. Okay, it's not accurate, completely accurate, but it flipped up and down, right? The same look. That's why a cubic's an odd function. When you take -x, it gives you -y. You can flip it left, right, or up, down, and you get that flippage. So you can describe one way. Oh, it says identify the parent function. I'd rather probably change a. I've mentioned this quite a bit. I prefer talking about a more so often than anything else. So I'm going to mention for that one there, I'm going to reflect over the x-axis. Reflecting over x-axis here would mean a is -1. Now you can put b as -1 as well, one or the other, and you'll see the difference in the equation. I'll write both and show you why I probably prefer a. But anyway, the a is -1. Okay. What else is happening to these points? Clearly there's a translation going on. But is there a stretch or compression? I don't think so. I think it literally just gets that 1128 business, but it's flipped over. So it looks like the rest is just a translation. You take the original centerpiece, you translate it 3 units to the right, translate 3 units right, and I think that's it. Translate 3 units right, which means the h is 3. So when we do this thing here, the original was f of x equals x cubed. Well, g of x is going to take our f of x. We're going to do -1 times f of x minus 3 like that. If f of x is x cubed, then f of x minus 3 is x minus 3 cubed. So g of x will be -1 times x minus 3 cubed. Or the way you probably see it written is negative x minus 3 cubed. And that is this graph right here. And that's with the a being -1. Alternatively, if I made b -1, if I said, hey, b equals -1, well, that's going to be now f of negative x minus 3 or negative x minus 3 cubed, and that can be a version of your answer. But if I simplified this, I would have cubed the -1 in front, and it would have turned into that anyway. So I personally prefer the a value there as often as I can use it. It's a more common, I know, oh, I'm sorry, you can't really see that. And I know, it's a more common thing to use there, a. B is nice, but it gets in the way of some of my talk sometimes. So I'm just going to kind of, let's just undo. Just showing you how you can use that, but I ain't gonna. All right, this is a square root, and like I said, as this is square root of x, I'm also going to do a version that is that's a quadratic. But f of x is square root of x as one of these things right here. Maybe you didn't know that it was a square root thing, but it is. In some capacity it is. Now the original square root, as you guys remember, it would have gone right here. So clearly there are some things that are going on. It's flipping over a couple ways. I think we talked about this in problem number 2. It flips to the left, and then it flips upside down, right? So if I reflect it over the x and y axis, then it would show up right here. It would have gone whoop, like that, and then gone on forward. Now these points in blue look like they are not stretching at all. So I'm not describing any stretches. It looks like it literally just translates upward. The green graph turns into the blue graph just by going 1 unit up after reflecting. So boom, it turns into that, right? I didn't draw perfectly, but that's the idea. So there are 3 things that happen. We reflect over both the x and y axes. Let me move myself. And you don't have to describe, but you need the equations. So we reflect over the x-axis. X-axis and y-axis. I should probably type this. And then we translate 1 unit up. So reflect over x-axis, that's an a of -1. Y-axis, that's a b of -1. Translate 1 unit up, that's a k of +1. So with f of x being square root of x, g of x, in the initial thought, g of x is -1 for a times f of -1 for b times x, hold on. Let me do that all over again. G of x is -1 for a times f of -1 for b times x, and then +1 right there. So there's no horizontal translation, it would just be that. As a square root of x, then it would look like -square root of -x plus 1. And I want to state one more time here, guys. In a square root, the negative cannot come out in that sort of way. Remember how I said that I would have cubed the negative inside here. The square root of -1 is I. You can't take it out and get real numbers from it. That negative has to exist inside there. These don't cancel each other out. This makes the graph go left. This makes the graph go down. Mr. Robinson, but here when you made the graph go left, flip over this way versus flip over that way, it changed. Yeah, it's a different kind of graph that does that. This graph, literally when it goes left, it's not the same as when it goes down. If I take this graph here and I say flip it over the y-axis, it's going to go that way. If I say flip it over the x-axis, it's going to go that way. Those are not the same graph as the cubic was. So that's a different story there. And that is the answer. There's no other answer I'm going to put. That is the answer there. But if I gave you an alternative graph to do, such as a quadratic right here, that originally, a quadratic as the original, and let's say I made it transform, let's say I made it look like, well, I'm going to keep the translation up here. I keep the translation right there, but I do want to flip it over. Let's say I gave you this graph instead, and I said, okay, tell me some stuff about it. How do you do it? It's going to be the same information. I want to make sure it's the same information here. Meaning translate 1 unit up and reflect over x and y axes. So notice the original graph would have been right here, right? The original quadratic would have been boom, boom, ba-boom, ba-boom. It would have gone upsy daisy. So what are the things you can do? You can take it, you can flip it left, right, and guess what? Same graph. You can flip it upside down after, over x-axis, and then it would have been right here, upside down, and then translate it 1 unit up. And that's where we are. So those 3 things still apply. A is -1, B is -1, which B is -1 actually literally means nothing for this. And I'll write that, I'll show you once again. A is -1, B is -1, and K is 1. This is an answer, but you really should simplify that thing here. You wouldn't have known one way or the other, B being -1. Flipping a U shape over changes nothing. So -x quantity squared is x squared, but the negative in front still applies because that flips this thing over. That's the best answer to that one there in green. So I'm giving alternative things to these because my kiddos have done quadratics but not square roots, and I want them to see something like that. All right, so that's number 12 there. 2 problems cracked in about 10 minutes. 2 more transformations, and I think we're done with all transformations after that. You don't have to hear them. Okay. Transform the given function f of x as described and write the resulting thing. This thing being a square root's no problem because we're not graphing it. You see a function, you do the things to it as we would before, and work it out. Expand horizontally is also the same thing as stretch horizontally, so I'm going to go ahead and write that. Stretch by a factor of 3. Horizontal stretch means b, or horizontal means b for that. A stretch means that 3 actually turns into 1/3. You take the reciprocal. That's what we're going to see in our equation. Translate up 3 units. Translate up is k, and k is 3 there. So g of x, the new transform function here, you're going to take your f of x, and you are going to take 1/3 of that guy, and plus 3. So that means that your actual g of x will be the square root of 1/3 x plus 3, like that. Again, you take your function that it is, the square root of x, and you're going to take the square root of 1/3 x, and that's what it's going to turn into right there. And that's the answer. You could also put square root of x over 3 like that. I prefer the number multiplied in front to reveal what your true b is or what your true a is. Okay, next one. Compress vertically by a factor of 2. That's the a value. And here's the thing. So notice how they did say 2 and not 1/2. But because they said compression, you know we're talking about that 1/2 nature. It's probably better what they put. I'll be honest. It probably is. That says twice as small. But the 1/2 to us is the telling of the a value. And I'm just going to go ahead and put that. A is 1/2. That's how I would have written it. Even though it's kind of a double negative. It's just like saying translate down -3 units. Shouldn't we just say translate down 3 units? Yeah. Anyway, a is 1/2, compressed vertically. Reflect across the x-axis. That actually has to do with a as well. Reflecting over the x-axis is flipping it over vertically. That means that a is negative. So this a of 1/2 is actually a is -1/2. Hold on, I just pressed a button I didn't want to. A is -1/2 right there. And that's all we're doing? It looks like it. So a is -1/2. So the original f of x was x cubed. You know, our g of x, we're going to take our f of x and multiply by -1/2. -1/2 times f of x. This was x cubed. Well, now it's -1/2 x cubed. And that should be the guy right there. And again, it doesn't matter what this function is. I could have made any function under the sun, functions you never heard of. Maybe you never heard of logarithms. I could have used that as well. That doesn't matter. You're plugging it in for f of x, whatever it is. Whatever goes in the input, such as 1/3 x, would take its place inside the function, whatever it is. Okay, I think that's it for transformations. Now we're going into function things, which I've done videos of before. These will go a lot faster. Perform the indicated operation. G of n is this, h of n is that. Find g of h of n. And that's what that means. This says g of h of n. H of n is the expression 3n plus 3. We're going to take g of 3n plus 3. That means 3n plus 3 will replace n in g's equation right here. This will become, instead of n cubed, it'll become 3n plus 3 cubed, minus, instead of 2n, it'll be 2 times 3n plus 3. Now, we probably do have to expand this, right? Otherwise, that's just a substitution. There's nothing else we do from that. But yeah, we expand this stuff right here. So we do have to cube this, unfortunately. So that equals. So cubing this, I'm going to go as fast as I can with that. You've done horizontal binomial expansion before here. A cubic in Pascal's triangle is 1331. So we cube the first term, and then we do plus 3 times 3n squared, or 3n gets squared to become 9n squared, and this 3 is to the first power there, plus 3 times 3n is to the first, and then the 3 is squared, plus the 3 gets cubed this time. So 3n quantity cubed is 27n cubed. 3 times 9 is 27, times 3 is 81. So 81n squared. Oh, by the way, I'm not done. This is minus 6n minus 6. The negative 2 distributes into there. 3 times 3 is 9. 9 times 9 is 81 here as well. 81n, and then plus 3 cubed is 27. And then you have minus 6n minus 6. I'm getting a little black blind here. I'm going to turn everything blue right there, because there's black right below it. Combine like terms, you get 27n cubed plus 81n squared plus 75n. 81 minus 6n. 27 minus 6 is 21, plus 21. I'll move that over. There you go. All right, there's an expansion. Now, f of x is negative 2x squared minus 4. G of x equals 2x plus 4. Let's do f times g of x, which does mean f of x times g of x. We are going to multiply those two quantities. That is what that means there. So f of x is negative 2x squared minus 4. G of x is 2x plus 4. Not a difference of 2 squares at all. Foil this thing out. Negative 2x squared times 2x is negative 4x cubed. Negative 2x squared times 4 is negative 8x squared. Negative 4 times 2x is negative 8x, and negative 4 times 4 is negative 16. And I guess that's it. No like terms to combine, and you're all good. All right, moving on. G of A is this, F of A is that. Find G plus F of 7. So that does mean G of 7 plus F of 7. That does not mean multiply 7 into G of A and F of A. You're going to substitute 7 in for A in these right here. So you can do this one of two ways. You can either combine, you can do G of A plus F of A first and then plug in 7. Or what seems to have been faster is actually do G of 7. I mean, we can write this out right now. Let's do this. G of 7 is 2 times 7 plus 3. 14 plus 3 is 17. F of 7 is going to be 7 squared plus 3. 49 plus 3 is 52. And then we're going to go ahead and get G of 7, 17, plus F of 7, 52, is, all right, 69. All right, no comment, moving on. All right, number 18. G of H of 4. That's literally what it is, G of H of 4. What you want to do here is, G of H of 4, we got to take H of 4. We got to figure out what H of 4 is right here. H of 4 is 4 minus 1, which is 3. So when you're taking G of H of 4, you're taking G of 3. G of 3. 3 substitutes for n in G's equation. That's 2 times 3 minus 2. 6 minus 2 is 4. G of H of 4 is 4. That's what that actually becomes. Hold on. Just gotta look. Okay. G of H of 4 is 4. Number 19. G of n is 2n plus 3. H of n is n squared plus 1. Find G of n minus 1 plus H of n minus 1. So n minus 1 is going to take place in both of these guys right here. I'm going to try and write this whole thing out and then combine things within. So that is going to be G of n minus 1 is 2 times n minus 1 plus 3 plus H of n minus 1. So this is going to be n squared minus 1. Nope. N minus 1 squared plus 1. There's the G of n minus 1. There's the H of n minus 1. And by the way, I'm going to bracket these just for a second. It's not going to be important for this problem. It's not going to change anything. But that's this plus that. It would be important if this was a minus, that this guy was grouped. Because that means you'd have to distribute the negative here. And yes, you would have to distribute the negative there when it comes to simplifying. But because this is a plus, there's no real effect to anything there. It doesn't actually change the result. Just please keep in mind, if it was, you'd really have to. All right, let's distribute some things out. This is 2n minus 2, and then plus 3. We got to do n minus 1 squared. That's a perfect square trinomial that looks like this. And then there's a plus 1 right there. Now we're just left to combining like terms, and I'll do standard form. N squared looks to be the first guy. I got 2n minus 2n, which is 0. And negative 2 plus 3 is 1. Plus 1 is 2, plus 1 is 3. I'm left with n squared plus 3 in the end. That's what this guy becomes. All right, G times H of negative 2t means G of negative 2t times H of course I read it G, times H of negative 2t. Okay. G of negative 2t is going to be negative 3 times negative 2t, that's replacing t, minus 2. And then we're going to multiply that with H of negative 2t. If you want to do these as separate steps and stuff, you can, and then multiply them after. But it's still going to be a binomial times a binomial, it looks like. H of negative 2t, that's 4 times negative 2t, that's replacing t, minus 3. Okay, negative 3 times negative 2t is 6t. So that's 6t minus 2 times, and this guy is negative 8t minus 3, like that, as you multiply those. So let's FOIL that out, and that becomes negative 48t squared minus 18t plus 16t. That's going to be negative 2t. And then negative 2 times negative 3 is plus 6. So that's the foiling business of that. Again, I did this. Boom, 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 boom. The negative 18t plus 16t I did in my head there to get you that one. All right, state if they are inverses. Now, there are two different ways that you can state something's in inverse here. You can use a composition of functions, or you can literally take the inverse of one or the other. Or you can look at this and clearly see that they're not inverses of each other. Let's start with the taking the inverse of one with the other and just see how they look. Now, here's the thing. Once you find out one's not the inverse of the other, you can say no outright. But I'm going to show you in every which way that this doesn't work. F of x means y, right? F of x means y. So I could say y equals 2x. I'll do this in a certain color here. Let's go in green. I'll say y equals 2x is the original function. If we flip-flop that, that becomes x equals 2y. And if you solve for y, you divide by 2, you get y equals x over 2. In other words, the inverse of that is x over 2. If g of x equaled x over 2, then these would be inverses of each other. Because the inverse of that is x over 2 and not x minus 1, they don't match. The answer is no. These aren't inverses. Let's do it with g of x. Let's call that as y equals x minus 1. Take its inverse, swap x and y. X is y minus 1. Solve for y, you get y equals x plus 1. In inverse notation, that's g. Whoopsie. In inverse notation, that is g, inverse of g of x equals x plus 1. Because f of x is not x plus 1, then this thing also is not an inverse there. You say no. So clearly those things aren't inverses of each other. As you take a look, you take one, you take the other. If one was a yes, I think you're supposed to take the other and see that it's also a yes. Same with composition. You can do composition of functions here as well. We can try and do f of g of x. And if we end up getting x out as a result, then it should mean kind of that it's an inverse of the other. We will not get x out as a result here, though, right? What are we going to get here? F of g of x means, I'll do it this way. No, I'll do it down. Means f of x minus 1. That's what g of x is. So we substitute x minus 1 in for x in f's equation. 2 times x minus 1, which is 2x minus 2. Because it doesn't equal x, that shows it's a no. And lastly, and remember, you don't have to do all 4 of these. You're really splitting this up. You're either doing a composition of functions here, or you're taking the inverse of one and the other. Alternatively, you could have tried g of f of x, which means g of 2x. And you're going to substitute 2x in for x right there. That becomes 2x minus 1. That doesn't simplify any further. That just says no. So if it equaled x, then they would be yeses. They would be yeses there. So we can try that on 22 as well. We'll see how much room I really have for all this stuff here. Let's start with these problems will take a while if I'm doing all 4 of them, especially how big these things are. Let's do the same color coding as before. F of x will be green. G of x will be purple. For f of x here, let's take its inverse. So y equals, here, I'm just going to go and swap, right? F of x means y. Let's swap x and y. So x equals, here's the inverse, negative 4 minus the 5th root. We haven't done 5th roots, but that's okay. You can raise to the 5th power of 16y all over 2. I'm going to start by multiplying both sides by 2 there. 2x equals negative 4 minus the 5th root of 16y. Got to add 4 to both sides there. 2x plus 4 equals negative 5th root of 16y. That negative is like a negative 1, right? So if we divide both sides by negative 1, what it's going to do is it's going to take that 2x minus 4, and it would change their signs. You could do, let's see, negative 2x minus 4 like that. And then that's, distribute the negative, right? Divide both those by negative 1, and that's 5th root of 16y. Then we'll raise both these to the 5th power. So to the 5th power here, and to the 5th power there. So that would then be the 5th to the 5th power. Negative 2x minus 4 to the 5th power equals 16y. And then you divide both sides by 16. And then you get negative 2x minus 4. Whoops. This is going to be a long problem to talk about. Negative 2x minus 4 all over 16. To the 5th power. That's why I had parentheses. All over 16 equals y. Now, that also in inverse notation. Listen, I'm going to have to erase this each time I do a new version of the problem. So the inverse, therefore, is that guy there. Let me try that again. I'm going to just erase everything and redo. So that would be the inverse is negative 2x minus 4 to the 5th power all over 16. Okay. Now you look at this and you look at this right here and you see that these two maybe don't match. And then you would say no. No, these aren't inverses of each other. Look, this is stupid. That looks nothing like this. Now I'm hard pressed to say one way or the other. I'm believing I know how this answer is going to look. You have to try and force a match. See, this one, clearly, there's nothing else I can do. X over 2 was not x minus 1. There's nothing, these are simplified as best as possible and whatever else. But this has a negative 2 that's factored out of here. You know, there's a difference between these two things. Now, what you cannot do in this problem here is I cannot factor, see, like, let's say I said, okay, negative 2 is factored out. Let's factor out negative 2 here. You do not factor negative 2 out of here and turn it into x plus 2 to the 5th power over 16. I can't factor a negative 2 out of the 5th power quantity. I can factor out of negative 2x minus 4, but it's still got to be to the 5th power there, right? I factored negative 2 out of just that part. I'm not done factoring things out, right? I factored it out, but it's still raised to the negative 5th power. So what can I do to get it out of the 5th power thing? I can raise it to the 5th power. It's a product. Negative 2 times x plus 2 to the 5th power. I can do negative 2 to the 5th power times x plus 2 to the 5th power like that. And then negative 2 to the 5th power is negative 32. And that's times x plus 2 to the 5th power right there. Negative 32 over negative 16 is negative 2. Look at that. Look at that. That is an inverse right there. They are inverses of each other. It's not no. The answer is yes. They are inverses of each other. And it takes this extra step to make that happen. It takes a little bit to actually match those things up here. Now, when I said I could have divided both sides by negative 1 right there, you know, I could have factored the negative 2 a hair earlier. I could have had the negative factored out, or I could have had this negative 2x minus 4, and I could have factored this negative 2 before raising to the 5th power. Then I would have raised to the 5th power. But you still have to simplify that negative 2 to the 5th power portion and divide by 16. That never would have changed. That would have still been the same right there. These are inverses of each other. And it took a little bit to make that happen, but it did get there. It did get there. And, you know, that makes it a little bit difficult. So, okay, there's a version of the answer. I got to erase everything. You're going to have to go back if you want to find this again. Let's find another version of the answer. Let's do g of x and try and turn it into f of x. Here's the thing. These are inverses. So what I just did does apply. If I do g of x, I should be able to match it to f of x, basically. But I got to work it so that it matches, right? Let's try g of x here. So let's swap x and y. Remember, g is y. Boom. So swap x and y. X equals negative 2 times y plus 2 to the 5th power there. All right, let's go ahead and solve for y all over again. Divide both sides by negative 2, and you get x over negative 2 equals y plus 2 to the 5th power. And then you can take the 5th root of both sides. Take the 5th root here, take the 5th root here. Right? I'm just making sure. Divided by negative 2. Yeah, I think so. And then you get the 5th root of x over negative 2 equals y plus 2. And then you subtract 2 from both sides. You get y equals the 5th root of x over negative 2 minus 2. Or the inverse of g of x equals the 5th root of x over negative 2 minus 2. Okay, that doesn't look like my f of x equation, so it must be a no, right? But I think we got yes last time. So what would we actually have to do here? What would we have to do to actually match these things up? Quite a bit. You have to consider, and I'm going to use this space, guys. Hey, I'm going to explore this stuff, man. This is some algebra stuff and saying, what if you were presented this problem? You know, just, yeah, what if you were presented this problem here? So inverse of g of x right there, that was the 5th root of x over negative 2 could also be the 5th root of x over the 5th root of negative 2. And I'll tell you what right here, I don't like that negative being in that denominator right there. It's no fun, but, you know, I'm going to work that thing out in just a moment here. And then minus 2 here. The 5th root of negative 2 is also the negative 5th root of 2. You can take the negative out of that because the 5th root of negative 1 is negative 1, right? So it can come out, which means it can also just be a part of the numerator. I don't even really need it as part of the denominator, right? It can be part of the numerator right there. There's a lot of algebra little tips and tricks that you can use based on that if it comes to cleaning this thing up. The other part of this is when it comes to matching this thing up with this, notice how 2 is a whole number here. This is 5th root of 2 down here. Clearly, this is an irrational denominator that can be rationalized. Now, you're probably used to, if I had over root 2, you're used to probably just multiplying top and bottom by root 2 and rationalizing the denominator. But the fifth root of 2 times fifth root 2 or fifth root 2, that doesn't rationalize it. That just becomes the fifth root of 4. And the fifth root of 4 is not a rational number. You need to find the first fifth power value that rationalizes this thing. That means we need to do the fifth root of 2 to the fourth. We need one more power of 2 to the fifth to make that work. And 2 to the fourth is 16. Rationalizing these denominators isn't quite as easy. It's not quite as easy as rationalizing square root denominators. So this would be the fifth root of 16 that you want to multiply on top and bottom right here. Fifth root of 16. There are other ways to talk about it. It has to do with fractional exponents, but you still have to get this ultimately. And you want this as a fifth root on top. Fifth root of 16 can't be simplified. On the bottom, this becomes the fifth root of 32. You know what the fifth root of 32 is? It's 2. So that becomes 2 down here, but on top has the fifth root of 16 multiplied by everything. So when we rationalize this guy right here, we are going to multiply top and bottom by the fifth root of 16. Fifth root of 16 over fifth root of 16. And that becomes, sorry for that little mark, these can multiply and become in one fraction, negative fifth root of 16 x all over fifth root of 32 is 2. And then I have minus 2 right here. Looks a little closer to this thing, still doesn't match. This negative 2 seems to be kind of this negative 4, but written out in front. How does negative 2 turn into negative 4? Well, I need a common denominator. I need to multiply top and bottom by 2, and that does turn into negative 4. So inverse, I did not mean to use that color, negative fifth root of 16x minus 4, and these are separately over 2. But of course, as a common denominator, you can put them all over 2. So I'm going to go ahead and put them all over 2. Kind of ease the load right there. And last thing, swap the negative 4 and the negative 16. So negative 4 minus fifth root of 16x all over 2. It does match up. It is a yes. And guys, that's a lot of work. That's a lot of work for these problems. Work that you probably would not have known how to do here. What's the moral of the story? Some problems are hard to do here. The other moral of the story here is when you want to state if functions are inverses, some people are turned off from doing the composition thing. And it might be easier to do. Doing the composition of functions might be easier to do. And I'm going to try that f of g of x, g of f of x, and see if it's easier. Listen, this is my first time doing this problem. I didn't anticipate that this would be this difficult. These take a while to do. But let's try the f of g of x and g of f of x approach and see if they go faster. See if they are actually just faster versions of these problems for myself. Because if they are, it's kind of a moral to the story that, you know, using the compositions do work out. By the way, when we do composition of functions here, we're going to see if f of g of x equals x, and we're going to see if g of f of x equals x. So let's go ahead and try f of g of x. F of g of x, which means we are going to be doing f of negative 2 times x plus 2 to the fifth power. Which means we're going to get negative 4 minus the fifth root of 16 times x, which is negative 2 times x plus 2 to the fifth power, all over 2. Okay, that becomes negative 4 minus the fifth root of 6, is negative 2? No, negative 2 is not to the fifth power. So 16 times negative 2 is negative 32. And then I have x plus 2 to the fifth power there, all over 2. Now, the fifth root of negative 32 you can take. That becomes negative 2. And the fifth root of x plus 2 to the fifth power becomes x plus 2. So fifth root of negative 32 would become negative 2 there. And then that fifth power goes away. So now this becomes negative 4 minus negative 2 times x plus 2, all over 2. Subtracting the negative becomes addition here. I can distribute that negative, but you can also turn this into positive. Negative 4 plus 2 times x plus 2 all over 2 there, which is negative 4 plus 2x plus 4, distribute, all over 2. Negative 4 plus 4 is 0, and you're left with 2x over 2, and 2x over 2 is x. So it does clean up, and honestly, that was a lot better than the other thing. Yes, That may have looked a little troublesome, especially with the negative portions, but I guarantee that was a lot better of a thing for me. Listen, the problem's just big. It just is. But that's a lot better for me to do. F of g of x there. Let's try g of f of x last and then kind of see how that thing goes. Okay, g of f of x. I used kind of dark blue last time. G of f of x will be g of negative 4. I don't think this one's going to be as fun. Minus 5th root of 16x all over 2. It might be, actually. We'll see. Plus 2. Oh, excuse me. Just that. Boom. And then we're going to substitute that in for x. So that'll become negative 2 times negative 4 minus 5th root of 16x all over 2 plus 2 to the 5th power. Like that. You'd work for a common denominator pretty immediately right here. This plus 2, I'm going to multiply by 2 over 2, and it turns into 4 over 2. So now as a common denominator, that's all one denominator inside of there. So I'm going to have negative 2 times, so all over 2 inside the denominator here will be negative 4 minus 5th root of 16x plus 4. Remember, that was 2 times 2. All raised to the 5th power. Okay, what I now have here is negative 4 plus 4 that goes away right there. And then I have inside of here negative 5th root of 16x over 2 raised to the 5th power. So let's raise both of those in a moment. That negative 2 over 2 can't cancel in any sort of way. 2 is to the 5th power inside there. So negative 5th root of 16x over 2 raised to the 5th power here. The negative 1 to the 5th power is negative 1. So just so you know, there will still be a negative that comes outside of here. It does not turn positive. This negative 2 will be multiplying some negative something. The 5th root to the 5th power will just leave you with 16x there. And 2 to the 5th power is 32. So you're left with that. Negative 16 over 32 is negative 1/2. So negative 2 times negative 1/2 x. Negative 2 times negative 1/2 is positive 1. You're left with x. X, yes. Once again, a function, or inverses of each other. Guys, that was a big problem. I did not know the problem was going to be like that. That was a big problem. I spent probably like 20 minutes doing that single problem, even more than the beginning ones. But there it is. Did a lot of that stuff there. I liked composition of functions a lot more than finding the inverses of them personally when it came to that ordeal of a problem. Listen, I didn't make this review. I'm not, that's all I'm going to say to that. I did not make this review. Okay. Let's keep that up. All right. Find the inverse of each function. These should be a little faster. Inverse of each function. Y equals negative 6x minus 9. Swap x and y. Negative 6y minus 9. Let's solve for y by adding 9 to both sides. And then dividing both sides by negative 6. X plus 9 over negative 6. Now, as far as an actual answer goes, we do not want our denominators negative. So you can either apply it to the numerator or apply it to the overall fraction. So the inverse of g of x, I'd rather write it as applied to the whole fraction on the outside. X plus 9 all over 6 like that. That's kind of my favorite version of the answer. That's what most answer keys would probably say. Otherwise, you can distribute the negative 1 into that, write it in factored form, yada yada, but do not have the denominator negative. Please don't have that. That's it. G of x equals, just like the irrational denominator things. G of x equals cube root of x minus 1 plus 1. That's y equals cube root of x minus 1 plus 1. Swap the x and y to take the inverse, and then solve for y all over again. Subtract 1 from both sides. X minus 1 equals cube root of y minus 1. Cube both sides now, and that becomes x minus 1 cubed equals y minus 1. Add 1 to both sides, we will get y equals x minus 1 quantity cubed plus 1 like that. And this was g of x as well, so the inverse of g of x equals x minus 1 quantity cubed plus 1. Those problems are not only a lot more fun, they're a lot, more approachable, but they also probably would have been for doing the whole check and see if it's an inverse of whatever its inverse is, even though, you got to plug some things in. Those are a lot more approachable than that problem. This problem was fine and very easy to see that they were not inverses. 22. Let's move forward. I'm already an hour 20 into this thing. Find the inverse of each function, then graph the function and its inverse. Okay. They did say find the inverse of each function first. I recommend that we do that here as well, because you might not know how to graph this cube root, and I would be hard-pressed to want to try and graph this cube root. It does not look like a fun one to do. So let's find the inverse right here. F of x will turn into y here, so y equals cube root of 4x over 2. Let's swap x and y, and for room's sake, I'm just going to do that right now. X equals, boom. And let's go ahead and solve for y again. Multiply both sides by 2. Cube both sides. Now, when I cube both sides, I'm going to go ahead and cube all of 2x, meaning I'm actually going to turn it into 8. 2 cubed is 8, so 8x cubed. If they want me to graph it, I'd rather deal with an a than a b. That's my personal preference. Given that we can fit it, we'll see if we can fit it in this problem. Equals 4y. Oh, yeah, we're going to divide by 4. Perfect. Divide both sides by 4. 8 over 4 is 2. We're going to get y equals 2x cubed. Or, and that's actually a really good reason why I wanted to cube that, or inverse of f of x equals 2x cubed. Okay, they ask us to graph the function and its inverse. Now, I don't want to graph that thing for many reasons. I mean, I'm going to have to at some point, but I'm going to start by graphing this guy right here. I'm going to graph this guy to start. I'm going to make this one green to kind of offset the color appearance. But let's start by graphing this guy because we know how to. 2 is like an a value, a stretch factor of 2, vertical stretch factor, make everything twice as tall. The cubic goes 1, 1, 2, 8, yada, yada. Well, this is going to go 1, 2 now, and 2, 16, well off the graph. I can't fit it. Oh, well. Negative 1 cubed is negative 1. Double that is negative 2. And then negative 16 down there. Can't fit it. So it's just going to be this big ol' cubic function, this really tall one that we don't really see the ends of this thing here, but it will hit into there. It will snake on through. Remember, it's not linear at all. It actually has that cubic appearance there. And that is the inverse that I graphed. How do I graph this? I don't even have to look at this to graph it. I can look at this graph right here and graph its inverse by doing what? Swapping x and y. When you graph the inverse of a function, it reflects over the line y equals x, over this line right here. You swap every x value into a y value and vice versa. And I'm gonna get rid of the dotted line afterward here. But 0, 0 swaps and becomes 0, 0. There's no change there. 1, 2 swaps and becomes 2, 1. Negative 1, negative 2 swaps and becomes negative 2, negative 1. Now, if you remember, these other points would have been 2, 16. Guess what? Now we would have had a point that was 16, 2. It would have been way over here. And I'm not going to actually plot it, but I'm giving the idea the graph is going to go that way. Negative 2, negative 16 will become negative 16, negative 2. It's off my graph over here, but this graph goes this direction right here, and it snakes on through like that, and let me try that again. But it snakes through that direction here. This is the inverse graph. You swap x and y. So even if you don't know how to graph the other one by its equation, you can take the other one whose equation you do know, and you can swap the x and y and then graph it. And that, folks, is how you can graph a function in its inverse. They reflect. If you turn your head the right way there, they are going to reflect over that line right there. They have that symmetry. When I remove the dotted line, they should still have that symmetry right there. Dotted line was just the aspect of it that helped you recognize what it is I was doing, and that's what I did. On number 26, this is a cubic already, so that means its inverse will be a cube root. So I'm going to graph this one initially when I do, and then I'll go ahead and graph its inverse as a result of swapping x and y. So I'm going to make sure to do that. I'll go and take its inverse right now. That's fine. Let's do swap x and y. X equals 2y cubed minus 2. Add 2 to both sides. Divide both sides by 2, and you're going to get x plus 2 over 2 equals y cubed. And then take the cube root, and we will get y equals the cube root of x plus 2 all over 2, or the inverse of f of x equals the cube root of x plus 2 all over 2. Now I'll tell you what. I know how to graph cube root functions. I wouldn't have had fun with this one, but I know how to graph it. You can use the a and the b and stuff like that and make that work. This one doesn't truly have our a and b revealed yet because the way that it's written, what I really should do with that, if we ever did come to graph this, is dividing by 2 is the same thing as multiplying by 1/2. So instead, inside of here, I would have written it like that, and that would have given us our b value. Our b value is 1/2, which actually means horizontally stretched by a factor of 2. And this is our h of -2, all that. I could have translated 2 units to the left. I could have stretched everything horizontally by a factor of 2, and we would have all been good. Because you know what the inverse is going to do? It's going to shift k. It's going to shift it 2 units down. Instead of 2 units left, 2 units down. That's swapping x and y. And it's going to vertically stretch by a factor of 2. Right? That's what this one says. That's what this one does. So anyway, yeah, it is an inverse there. That's how I would have actually written it ultimately. This is fine. I guess we're taking its inverse if you're not trying to graph it here. But this is a better answer if it came to you knew how to graph it and you wanted to. Anyway, let's go ahead and take this first one here, graph that. I'm going to shift my center 2 units down. That's k. And this x cubed here, 1, 1, 2, 8. We're going to double those values. 1, 2, 2, 16. It's like the other one, right? 2, 16, I can't fit there. -1, -2. -2, -16, can't fit it. Boo hiss. We'll go ahead and sketch that cubic. This is the original function here. Now, the inverse flip-flops the x's and y's. Any point that you see on here, flip-flop it. You'll get the inverse guy. I don't need the blue line, that dotted line to show that, but that's what it reflects over. So you see the point 0, -2? There should be a point -2, 0. And that makes sense because our center of this cubic, instead of 0, 0, it's going to shift 2 to the left. That's what that h is telling you. Instead of a point 1, 0, we'll have a point that's 0, 1. Instead of a point that's -1, -4, we'll have a point that's -4, -1, like that. And remember the whole 2, 16, well, this would have been 16, 2, and -16, -2. So this thing is going to kind of take off in that cubic nature outward to that 16, 2, boom, like that. And then on the other side, it's going to snake on through and come out that version. I can do better than that. Normally I come from the end. Let's do that. Let's come from the end there. It's going to make it a little bit easier to do what I want to do there. And snake on through and out that direction right there. There we go. So there's my cubic. If you turn your head in the proper direction, you're going to see kind of that the thing there. So yeah, and so just like I said, this thing is horizontally stretched by a factor of 2. Normally it would have gone 1, 1, 1, and 6 and 8, 2 like that, but now it's 2, 1, and 16, 2, as it's horizontally stretched by a factor of 2, as the b of 1/2 does reveal. And those are those 2 graphs there. Perfectly valid problems. Perfectly valid problems to do. Unlike that, other problem where we were doing that inverse stuff, this is a totally approachable and okay problem. All right, for each function factor. Okay, so they're asking us to factor and they give us no room. So I'm going to have to do one problem at a time, guys, and I'm going to have to erase it each time. So because otherwise I'm not going to have any room on this thing. So you're going to have to accept the fact that you have to rewind it to find those actual questions here. And I'm going to white out all the other stuff here. So I'm going to start with number 27, and then we'll try and do all the information they want. They even want us to sketch the graph. I don't know where you're going to have room for this stuff. Factor, then state the maximum number of turns the graph could make, determine the real zeros, and state the multiplicity of any repeated zeros. List the x-intercepts where the graph crosses, and sketch the graph. Okay, so this first one right here, let's start by factoring. I got a GCF right here of -2x squared. No, I'm sorry, just -x squared. Of -x squared. And then I'm left with 2x squared plus 5x minus plus 3. And then this thing can factor down, hopefully, right here to 2x and x with a 3 and 1, plus 1 plus 3. 2 plus 3 is 5. And that's what this thing factors down to. This is the factored form. Okay? So that is f of x. Check. Boom. Factored. State the maximum number of turns. Now, I'll do that after I graph. I'm going to talk about that thing here in full, but being a quartic, you'd want to look at this to kind of tell you what it is. Being a quartic, I'll tell you there will be 3 maximum possible turns that the graph could have. Actually, I have to be careful in saying what I just said because maximum number of turns could make is different from how many it will make because a multiplicity of 3 could occur. But anyway, yeah, you know what? Yeah, let's go to answer that now. It could make 3 turns. What do I mean by turns? I mean a quartic could look like that. It can turn once, twice, 3 times. These are relative extremes, relative mins and relative maxes. That's what they're asking. How many relative mins and maxes could a quartic have at most? Now, how could it have less? It can't have more than 3. How could it have less than 3? It could have had, sorry about that. It could have had 1 turn. It could have just done that. Quartic functions can do that. Like a quadratic. I don't know why that keeps erasing. It could also have behaved like a cubic. It could have had that cubic nature on one portion there, and it could have turned back up, and that it does not count as a turn. A turn is a relative max or min. A turn is a change in direction from positive to negative, increasing to decreasing, or decreasing to increasing right there. That's only 1 turn as well. So 3 turns at max, otherwise it could have done some of these other things right there. A little tricky. All right, determine the real zeros. Now that is based on factoring right here. If I set this guy equal to 0, I find the real zeros here, and I'm going to get x equals 0 as one of them. 2x plus 3 equals 0. Subtract 3 divided by 2. You get x equals negative 3 halves as another. And x plus 1 equals 0. X equals negative 1 is the other 0 right there. 3. List the x-intercepts and the multiplicities of any repeated zeros. 0 is one of them, and that has a multiplicity of 2. That's where you see that x squared. Multiplicity of 2 right there. That x squared means it'll bounce off that 0. Negative 3 halves is the other one, and then negative 1 is the other one. No different multiplicities. That's all that they are. And then 4, sketch the graph. Now, there's something else that I wish that they talked about. State the degree of the polynomial and the sign of the leading coefficient. That's where the graph also happens to be. Being a quartic means it has either start up, or start down, end down behavior. The end behavior, and list end behavior. 5, list the end behavior. I didn't make this. So list the end behavior. So all those things kind of come into play here. I'm going to try and sketch the graph based on all those notions, and I'll tell you about them with these features. Stating the zeros and then the x-intercepts and multiplicities, those are the same thing to me. So as far as these things go right here, I'm sketch a little rough sketch graph here. We got to hit not too many values here. Here's 1 and 2 and negative 1 and negative 2 and all that jazz. This thing is going to hit 0, negative 1, and negative 3 halves, which is negative 1.5. This is a negative quartic, which means it'll start down and finish down. Whatever it does here, it's going to do that with some in-between character. So hitting negative 3 halves right here, it's going to hit and cross through. Then it's got to come back down and hit negative 1, and then it's going to bounce off of the 0 right there, and then finish downward like that. That's a sketch of the graph. That's a sketch of the graph right there. How many turns did it make? 1, 2, 3. It could have made 3 turns. It made as many as 3 turns. We got it sketched. The y-intercept, by the way, is 0. I know I talked to my students about y-intercepts. The x-intercept is 0, therefore the y-intercept is plus 0 for the constant. The y-intercept of that is 0. The end behavior, as x approaches negative infinity, y approaches negative infinity. As x approaches positive infinity, y approaches negative infinity. Negative leading coefficient, quartic, 4th power, even degree. That's what it does. All right, that's number 27. I have to erase it to do with the other ones here. You can do this on a separate sheet of binder paper, I suppose, to fit it all. 28. Oh, the only one that's erased. 28. Another quartic. Let's get rid of all that. Another quartic here. Factor. Let's start by factoring. It's already checked as if I've already done it. No GCF. So we need our P's over Q's here. We need to factor, not by grouping, we need to use rational root theorem here. P's over Q's. Factors of 2 divided by factors of 2. That's 1, 2, and 1/2, positive and negative. We're going to test values of these and see which ones give us 0. I'm going to start with 1. 2 times 1 to the 4th, that's 2. Minus 1, that's 1. Minus 6, that's negative 5. Minus 1 plus 2, that's not 0. Negative 1. 2 times negative 1 to the 4th is 2. Minus negative 1 cubed, that's plus 1. That's 3. 2 plus 1 is 3. Minus 6 is negative 3. Plus, minus negative 1 is plus 1 is negative 2. Plus 2 is 0. So negative 1 will give us a 0 right here. We can use synthetic division on that guy right there. We'll get 2, negative 1, negative 6, negative 1, and 2. Very fair question here for factoring. I love it so far. 2, negative 3, negative 3, 2, and 0. So, so far this factors into, if negative 1 is a root, then it's also an x-intercept. It's a 0. X plus 1 times 2x cubed minus 3x squared minus 3x plus 2 is that factorization. This still does not factor by grouping. It's still a cubic. It's not a special case. We have to do rational root theorem again. We can use these same zeros. Keep in mind, we already tested 1. 1 did not work. 1 will not work this time, therefore. Negative 1 did work. Negative 1 could work again. It is worth testing. And by the way, where am I testing? Right here. I want to see what f of negative 1 is. We can plug in negative 1 into these. We'll get negative 2 minus 3 is negative 5 plus 3 is negative 2 plus 2 is 0. Negative 1 worked again. And that might be the only rational root. Well, actually, I doubt it. We're probably going to factor this down to all rational roots. So I'm sure 2 and negative 2 may work. 1/2 negative 1/2 may work. But we have to, well, you don't have to test negative 1, but you got to test all rational roots. You got to test all possibilities. You can't skip it. If this was the only one left, you had to have tested it. So 2, negative 3, and 2. Looks like it was calling out to me that negative 1 should have worked. All right, so we're left with that. So now this is factored to what? This has a factor of x plus 1. That has a factor of x plus 1. That means that x plus 1 squared is, x plus 1 times x plus 1. X plus 1 squared is of the factorization that exists there. This x plus 1 squared. And this is 2x squared minus 5x plus 2. And that factors into 2x times x with the 2 has to go here and the 1 has to go there. Negative 4 minus 1 is negative 5. So there's the factorization of this whole thing. We factored. We are set on that piece. And I'm really exploring this space. So we're set on that. All right, what are some other things we have to do? We have to determine the number of turns. This was once again a quartic. The number of possible turns could have been 3. One less turn. There's one less turn than there is degree of the thing as a possibility. So there's that. The number of zeros and x-intercepts. Those are, I'm not saying they're the same thing, but they are. X-intercepts are a coordinate pair. Negative 1, 0, 5, 0, things like that. That's literally what they are. But as far as what we're doing here, I want to just state x-intercepts in their multiplicity straight up. So negative 1, that is a multiplicity of 2. That part's squared. The next one is 2x minus 1 equals 0. If you add 1 and divide by 2, you get x equals 1/2. So 1/2, that is a multiplicity of 1. And then 2 right there. And then sketch the graph. So sketching this graph here, negative 1, 1, and 2, boom, boom. Okay, it's going to hit negative 1 here with a multiplicity of 2. It's going to hit 1/2, which is right there. It's going to hit 2 right here. This is a quartic, a positive quartic function. It'll have start down, finish up quality. Start up, finish up quality like that. So it will cross through, it'll bounce off negative 1 with a multiplicity of 2 right here. It's going to come back down through 1/2, and it's going to come up through 2 and swing and a miss. An air ball, if you will. Another air ball. Take it for what it is. There we go. That's what I always intended. There's that graph. There's the idea of that graph. Now, they did not ask for y-intercept, but I'm going to give it to you. Where is that crossing the y-axis right there? Look no further than this constant, 2. When x equals 0, y equals 2. And there's the y-intercept right there. That seems to align with everything else. There's the graph. It made 3 turns once again. 1, 2, 3. Relative maxes, relative mins, right? This was a relative min, relative max. Okay, that was number, I think, 28, I think. By the way, I think this is the last page for all this stuff. Everything that you're looking at, I believe we are on the last page. So not much more to go. Up to 34. I want to finish by the 2-hour mark here. I did not anticipate this to be this long, but you know what? Videos go on as long as they have to. You don't want to watch? Don't watch. All right. Negative x to the 4. All right, I see a GCF, not only the negative, but also x right here. You can factor an x out of this thing and the negative, and you have x cubed plus 4x squared plus x minus 6. This, rational root theorem, p's over q's, plus or minus 1, 2, 3, and 6. Factors of 6 over factors of 1. This one right here. We're testing inside there, right? Let's try 1. 1 plus 4 plus 1 minus 6. Yes, it works. So let's use synthetic division on that 1 right there. So 1x cubed plus 4x squared plus 1x minus 6. I've liked these problems so far. I did. I wish the instruction talked about end behavior and leading coefficient and y-intercepts and relative maxes and mins, and didn't have to double up on the x-intercepts and the zeros. But I like the problem so far. I like the factoring. I wish we had different factoring types, but these are good. These are good practice. Okay, so right now, this thing is factored into. There's the negative x. The 1 root would leave us with an x minus 1 factor, and this is x squared plus 5x plus 6. So now, x squared plus 5x plus 6 factors into x plus 2 times x plus 3. Okay, that's a fun graph. So we have the following x-intercepts here. So there's factored form, by the way. F of x equals factored form. We have the following x-intercepts here. 0, 1, negative 2, and negative 3. All multiplicities of 1. As a quartic, it can only cross through the x-axis 4 times at most. That's also why it can turn 3 times. Cross through 1, turn, cross through 1, turn, cross through 1, turn, 3 turns, cross through 1, finish. Okay, and let's just go and sketch the graph from there. I can talk about end behavior and stuff with it. This was a negative, by the way. This was a negative quartic, start down, finish down. This is what we're going to look at. Touchdown. Negative 1, negative 2, negative 3. I need to fit that. And for symmetry purposes, I'm going to put 1, 2, 3, even if we don't go that far. This thing starts down, finishes down. It crosses at negative 3, at negative 2, at 0, and at 1. It probably has a little bit of symmetry, not across the y-axis, but just when it kind of goes up and down right here. I can't guarantee that, but it probably does this like, whoop, and then it just repeats that. Like it probably actually bottoms out at x equals negative 1. It probably hits this relative minimum down there. But it goes ahead and does that. And my curves aren't perfect. My technology that I have is not always helping right there. But 3 turns once again. Oh, 3 turns, by the way. For a quartic, 3 turns. 2 relative maxes and a relative min. By the way, global maxes, extremes, global extremes, absolute extremes, these have absolute maxes. This has an absolute max somewhere. Maybe both of these are the same height as I talked about symmetry. But there's that as x approaches negative infinity, y approaches negative infinity. As x approaches positive infinity, y approaches negative infinity. And the y-intercept is 0. All right, that is that problem there. Let's do one more of this accord. Let's see if it's something that's not just rational root theorem with a quadratic. Where is it? 30? It's rational root theorem again. Definitely looks like it. We'll deal with it. All right, number 30. Factor out a negative though, right? Always begin with that. So f of x, or not always factor out a negative, but if your leading term is a negative, please, please, please factor it out. And if there's anything else to factor out, please, please, please do so. It's a part of your full factorization. They asked us to factor. This is a part of it. All right, rational root theorem right here on this guy. We're going to do p over q, factors of 6 over factors of 2. So plus or minus 1, 2, 3, and 6. What am I doing? 3 and 6. And then divide some of these numbers by 2. 1 divided by 2 is 1/2. 2 divided by 2 is 1. We have that. 3 divided by 2 is 3/2. 6 divided by 2 is 3. We have that. These are the possible rational roots that will come to be. We're obviously going to test 1, negative 1, things like that. I'm hoping for something small to start. Let's see. Plug in 1. 2 minus 5 is negative 3. Plus 1 is negative 2. Plus 6 is not 0. Is 4. Negative 2 minus 5 is negative 7. Minus 1 is negative 8 plus 6. No, that doesn't work. 2. All right, now we got to do this. 2 cubed is 8 times 2 is 16. By the way, I don't care what this is here. I care about what's 0 here. So 16 minus 5 times 4 is 20. 16 minus 20 is negative 4. Plus 2 plus 6. Nope, negative 2. My ears were popped. Hold on. Try to pop my ears. My ears were plugged. Negative 16 minus... okay, that's not going to work. Trust me. 3. 27 times 2 is 54. Minus... Hold on. I want to make sure I factor out the negative correctly. I'm not saying I didn't. I didn't factor out the negative correctly. Guys. Hello. I wish I could take this out of my video. I just rewrote the whole thing. I was looking at those things and going like, I felt like the 1 and stuff should have worked. Like I was close if only one sign was different or whatever. I didn't factor out the negative. I'm sorry. I did, only for the first term. I pulled a student thing. I airballed again. Let's try 1 again. 2 plus 5 minus 1 minus 6. Yes, 7 minus 7. Okay, 1 works. You guys probably saw this and you're like, did I do something wrong? Is he going to fix that? I wonder if 3 would have worked as a false reason. That would have sucked. I don't want a false positive. All right, 2, 5, negative 1, negative 6. I've been at this for an hour 45. Deal. Whoa, something flashed on the screen behind me. Epileptic warning. Here we go. I never do that. I never do that. And yet, I did. I'm losing my touch. All right. X minus 1 is a factor. So f of x equals x minus 1 times 2x squared plus 7x plus 6. All right, I'm going to factor that like a beast right here. You know what? I did so much factoring. I factored 278 problems the other day. You got to forgive me for botching 1. I wonder if I did that the other day as well. 2x and x. Plus 2 and plus 3. So 4 plus 3 is 7 right there. And all is good. See, negative 2 should have also worked. All right, so there's the factored form right there. And it looks like negative 3 halves will also work. So yes, what are we going to talk about? Number of turns. This was a cubic. It can only turn at most twice. Boom, boom. At most 2 turns. I'm just answering that one out loud. I'm going to move myself. Give me a second here. So 2 turns at most. Okay, just make sure I'm in the shot, or this stuff's in the shot. Intercepts. X-intercepts are 1, negative 3 halves, subtract 3 divided by 2, and then negative 2. Multiplicities are all of 1. Let's go and sketch the graph from that. Sketchity sketch. Right here, we're going to cross through negative 2, negative 3 halves, that's negative 1.5, and 1, like that. It's a negative cubic. It'll start from the top, and it'll finish downward. So it's going to start from up here. It's going to turn back right here. Boom. There's a turn back. And there's another turn back here as it goes ahead and hits there. It has 2 turns, a relative min and a relative max right there. No absolute extremes for a cubic. And it hits a y-intercept, by the way, of 6 right there. And there's the graph. As x approaches positive infinity, y approaches negative infinity. As x approaches negative infinity, y approaches positive infinity. And that is number 30. All right. We're done with those things there. Let's see what is left on this. Just delete everything. All right, divide. Now, division's not a part of really this unit, but I'll go ahead and do them. And really, you got to use long division on these. So I need a little bit of room. I'm going to clear this out. And I have to do one at a time, really. 4 questions in 12 minutes. I think I should be able to do that. I just got to rewrite this thing here. 6x to the 4th minus 12x cubed. And listen, you got to know how to do this stuff. Minus 11x squared plus 16x minus 10. You will probably want to know how to do long division for the next unit on graphing rational functions. Sometimes you got to get sometimes you have to divide. X squared goes to 6x to the 4th, 6x squared times. You multiply that, you get 6x to the 4th minus 12x squared. I want to line that up over here. And I'm going to subtract these results. You get negative 12x cubed here. Negative 11x squared minus negative 12x squared is positive 1x squared. And you get plus 16x minus 10. We're going to do this 2 more times here, because x squared can go into an x cubed and an x squared after. This will go in negative 12x times. We get negative 12x cubed. Negative 2 times negative 12x is positive 24x. Line that up there, because that's where they'll combine. and you get x squared here minus 8x as we subtract that, minus 10. X squared minus 2 again. X squared goes into x squared one time, and then that's x squared here. Negative 2 times 1 is negative 2. And subtract that, you get negative 8x, and negative 10 minus negative 2 is negative 8. So that's the remainder. X squared can't go into an x any number of times. So your final answer here is a quotient. It will be 6x squared minus 12x plus 1 with a remainder of, now you can do one of two ways, either plus negative 8x minus 8 all over x squared minus 2. I don't know if I prefer that plus there. I'd rather almost factor out, this is trying to match an answer key, and I don't know what the answer key is going to say, but they might have factored out a negative 1 and turned this into a minus, so this becomes minus 8x plus 8 like that. That's another version, what I just wrote or what this one is right here, and that would be the remainder. If you could try and factor, like you could factor an 8 out of there as well, and if you could divide with something on the bottom, difference of two squares, anything like that, that'd be cool. That does not happen here. Okay, the next one. Wait, write your answer in fraction. Oh, this is fine. That's fraction. I think they're talking about the remainder there. And expect some remainders on these. Normally when someone else is making the review, they tend to have remainders as their answers. So this one does right there. Let's clear this out again. Do one more division. Long division here. Make sure it's in standard form. It looks like it is. And we get 4x to the fourth plus 22x cubed plus 4x squared plus 23x plus 8 divided by x squared plus 6x plus 3. X squared goes into 4x to the fourth, 4x squared times, multiply that, you get 4x to the fourth plus 24x cubed. 3 times 4x squared is 12x squared. Subtract, that's negative 2x cubed. Subtract, that's negative 8x squared plus 23x plus 8. So we get x squared plus 6x plus 3. X squared times negative 2x cubed is, sorry, not times, times negative 2x is negative 2x cubed. And then you get negative 2x cubed from that. Negative 12x squared, and 3 times negative 2x is negative 6x. I don't know why this is in the review. We get 4x squared there, subtracting the negative. Subtracting this negative is 29x. And plus 8, hoping I'm not making a little mistake here or there. One little slip up obviously changes the whole entire spectrum of the answer, and hope I'm not getting that. X squared right there, and 4x squared plus 4. So 4x squared here, 6x times 4 is plus 24x, and 3 times 4 is 12. Looks like we'll get another remainder as we get 5x here minus 4. So there's the other remainder. X squared cannot go into x, so your final result will be this quotient with that remainder. 4x squared minus 2x plus 4 with the remainder of 5x minus 4. That's all over x squared plus 6x plus 3. So there's that final result. I don't see any other version of the answer that you would have unless my answer is wrong. And I don't believe that it is, but it could be. All right, 7.5 more minutes just to do these here. Write a possible equation for this polynomial in factored form. Assume assume A is 1 or negative 1. I'm sorry. Assume a what? Assume A is 1 or negative 1. And the reason they say that is just so you can, you don't put another number in for A, and no one else here would. Now, how do we decide whether it's 1 or negative 1? End behavior. This looks like an odd degree function, and that'll deal with itself when we talk about multiplicities, but it looks like an odd degree function, finishes downward. It's going to be negative. A will be negative 1 in this scenario. The A is just the thing that comes out in front of the factored form of whatever. We're going to have a negative out there, and that's what I'm about to do. So what do we do here? We work backwards from what we had in the previous kinds of problems. We look at where these x-intercepts are, and we look at their multiplicities. It has x equals negative 2 with a multiplicity of 2 as a bounce back. That means that in this function here, we do have a negative, and we have a factor that's x plus 2. It touches negative 2, and has a multiplicity of 2. That's one of them. Then it comes back down, and it hits 0 right here. That's where x is, and that is also bouncing off. So this, I'm going to put the x in front, that's negative x squared. And then it hits 1 right here with a multiplicity of 1. It just goes straight through. It doesn't snake through like a cubic, and it just goes straight through. It doesn't bounce off. So that's x minus 1 right there, x minus 1. Now this it's only asked for factored form, and their factored form is, I'm going to appease the standard form crowd, and I will go ahead and expand this thing as well. But they only ask for factored form. Standard form, I'm definitely going to start by expanding the x plus 2 squared. I always want to do things the fastest way that I can. And for me, it's leaving the negative x squared till the end and working out pairs that are of best case for me. X squared plus 4x plus 4, you betcha. That's multiplying by x minus 1. So now I'm going to distribute these together. Keep the negative x squared on the outside. I'll get x cubed minus x squared from those two. And then plus 4x squared minus 4x for those two. And then plus 4x minus 4 for those two. Negative 4x plus 4x is that. Negative x squared plus 4x squared is 3x squared. So now I have negative x squared times x cubed minus, no, it's a plus, plus 3x squared minus 4. And now we get to distribute the negative x squared. That's negative x to the 5th minus 3x to the 4th plus 4x squared. So that is the standard form version of this guy, standard form. And let's see if at least some things agree. It is obviously negative right there, but it's also a quintic. It's a fifth power that's an odd degree. Like I said, it will take care of itself. If you indicate the right multiplicities and you have as many zeros, as many x-intercepts as there are, being an odd degree will take care of itself through your formula, through your thing there. So it naturally is that it was negative. It does finish downward. There it is. With a negative 1, with a negative 1a value. If this was negative 2, clearly some of these numbers get doubled. All right, and last problem here before the 2-hour mark hits, write a possible equation in factored form. Of course, I guess assume a is 1 or negative 1 once again. Same stuff. So right here, let's figure out our intercepts and their multiplicities. Let's use green. X equals negative 4 with a multiplicity of 1 means x plus 4 is a factor. X equals negative 2 with a multiplicity of 1 means x plus 2 is a factor. X equals 0 means x, by the way, this is a positive. It's positive in even power. X is a factor there, and not x squared. It just goes straight through. X is a factor as x equals 0. X equals 3 means x minus 3 is a factor. It has a multiplicity of 2 as it's squared there. And then x equals 6 means x minus 6 is a factor here. Standard form is going to take a lot more to do with regard to expansion. I'll wheel and deal. I might not finish by the 2-hour mark now, even though if you want to finish, guys, that'll do it. This is Mr. Robinson. Take care. I'll see you in the next one. For those who want to see standard form, let's keep going. Past the 2-hour mark, we go. So I'm going to leave x till the very end here. I'm going to expand what I can as fast as possible regarding stuff. I like to leave x till the end because it's a GCF. It's my way of dealing with things. Let's go ahead and do the x plus 4 times x plus 2, though. I'm going to treat those two together. Boom, boom. I'm going to square this on its own. And here we'll get x squared plus 6x plus 8. Here we'll get x squared minus 6x plus 9. And this is x minus 6. So there's still a lot to do. 2 trinomials multiplied, and then I'll multiply the binomial by that result. So let's multiply the trinomials out. How about that? X to the 4th minus 6x cubed plus 9x squared plus 6x cubed. This is here. Plus 6x cubed minus 36x squared plus 54x plus, plus 8x squared, I am a trooper, minus 48x plus 72 for the crowd still watching. If this was a live stream, everyone's gone. The x cubed, negative 6x cubed plus 6x cubed is 0. 9x squared minus 36x squared is negative 27x squared plus 8x squared is negative 19x squared. So negative 19x squared. 54x minus 48x is 6x plus 6x there. So we should have, if I didn't mess anything up there, that should be x times, I'm going to write the x minus 6 next. X minus 6 times x to the 4th, no x cubes, minus 19x squared, that's good, one less term, plus 6x plus 72. Now we got to do the x minus 6. You know what, I'll go and do the x squared right now. It doesn't change really anything there. It's going to be x squared minus 6x times blah, blah, blah. All right, here we go. Last bits. We're going to have x to the 6th minus 19x to the 4th plus 6x cubed plus 72x squared minus 6x to the 5th plus 114 x cubed minus 36x minus, oh, hold on, did I change signs correctly? Yes, minus 6 times 72 is 432, minus 432. So, f of x equals, last one, ooh, 40 seconds, let's see, x to the 6th, minus 6x to the 5th, minus 19x to the 4th, plus 120, x cubed, plus 72x squared, minus 36x, minus 432. There's my standard form. All right, and I think I beat 2 hours, 15 seconds left. That ought to do it for this one, guys. This is Mr. Robinson. Thank you so much for watching. Listen, this video did not kind of fully go as planned there, but I'm sorry about that. Hopefully you learned some things along the way, maybe paused it. But hey, guys, take care. I'll see you in the next one.